Okay, so good afternoon, everybody. Let me say first a few words in Hungarian before we switch to English, because not everybody knows what it is about. Üdvözlök minden kedves résztvevőt, én Radnóti Gábor vagyok, és engem ért a megtiszteltetés, hogy a Dévényi Dezső emlékére alapított ezévi ünnepi ülését levezessem. Az ülés angol nyelven fog lezajlani, lévén, hogy Dezső munkásságának utolsó szakaszát Amerikában, a colorádói Boulderben töltötte, és jó néhány ottani barát és kollega csatlakozik a mai rendezvényhez. És akkor mostantól angolul fogunk beszélni. So let's switch back to English now. My name is Gábor Radnóti, and I have the honor to chair this event, namely the Dezső Dévényi Award ceremony. Dezső was my friend and colleague, and if I may say so, he was a kind of mentor for me as for many of us at the Hungarian Meteorological Service. This dates back to the time when I started my professional career at the newly formed small group of numerical weather prediction at the Hungarian Met Service back in 1986. Later, both Dezső and I moved on. Before my retirement this year, I spent the last 2 decades at ECMWF. Dezső has visited us at ECMWF a couple of times. For the last time, just a few weeks before his death. That time, he gave a seminar on his most recent work at NOAA Earth System Laboratories in Boulder, Colorado, where he was a data simulation expert in the final stage of his scientific career. When he came to Reading, he still had a lot of plans and ideas, and during this last visit of him at ECMWF, he had discussions with our data simulation and satellite teams. He wanted to learn all details of the humidity control variable and how all sky radiances and rain-affected satellite data are assimilated at ECMWF, how our colleagues are doing this. Dezső and I shared a lifelong passion and interest in football. And during this last visit of him, we managed to go to see together a Premier League game between Birmingham and Manchester City. And I'm quite sure that now, if Dezső was here, he would say something like, "Hey guys, how on earth could you schedule this meeting in clash with the World Cup game between Portugal and Morocco?" In a minute, you will hear more details about. In a minute, you will hear more details about Dezső's scientific career and achievements from Stan Benjamin. Stan was Dezső's colleague and good friend at NOAA Earth System Research Labs, earlier Forecast System Laboratory, in Boulder, Colorado. Stan, now a few words about Stan to introduce him. So he got his MS and PhD in meteorology from Pennsylvania State University. At the beginning of his career, he spent a number of years at NCAR. And until his retirement later, he worked for NOAA ESRL, where for more than 25 years, Stan was the chief of assimilation and modeling branch, later the Earth modeling branch. Stan, as a good friend and colleague of Dezső, has kindly accepted our invitation to the committee of the award and for this occasion, he offered us to give an introduction about Dezső. So now I would like to ask you, Stan, to give your introductory presentation.
Thanks very much. Köszönöm szépen. Dezső was a key colleague to us in Boulder, in NOAA, and he really enabled some key developments happen with numerical weather prediction that actually has an influence even today. Today in NOAA, our hourly updating model is the high resolution rapid refresh model. And what Dezső did in the top bullet there was critical to enable this data assimilation work. Before he worked with us, he wrote an important masterful book in mathematics and statistics that I will show about later. He got his PhD from Eötvös Loránd University in Budapest. He had important roles with the Hungarian Met Service, even as the vice president or deputy director, as Gabor and András Horányi can speak of, and many others. He taught numerical weather prediction in Hungary and was really called even the father of NWP there. So he helped us develop some very key data assimilation capabilities. On the right there, the picture of Dezső, he had in his signature this very peculiar phrase, "I agree that it works in practice, but how can we be certain that it will work in theory?" That was the backward kind of thinking that Dezső always brought to all of us in thinking about things. Next slide, please. So it was in 1989 that I first met Dezső at an IUGG meeting at Reading. And 2 years later, Tom Schlatter and me visited Dezső in Budapest. And I have some pictures to show about that. A few months after that, Dezső started his first tour in Boulder for a couple of years through the National Research Council. He helped us do a couple of data assimilation things. I'll speak more about that later. But then he came back for 2 positions through the University of Colorado, the Cooperative Institute series, and ended up with 16 years total at GSL. So an important time period with all of us. Next slide. In our visit in 1991, Tom and I visited with Dezső. It was wonderful to be able to see the role that he had there. And there was a picture of Gabor at that point and me with my eyes closed. But it was an honor to be able to see what was taking place at the Hungarian Met Service and to see his setting. And we gave seminars there. Next slide. So Dezső, again, had such an important role. Some more pictures here with Tom and also with András on the lower left, and then with Gabor on the right. These are all pictures that Tom took on his camera that we just got available over the last few days. So our time together goes back, went for 20 years, and then we remember back to this very fondly. Next slide. So I wanted to speak about Dezső's main accomplishments, and both the first 2 had to do with data assimilation goals that we really could not have done without Dezső, and the third one has to do with convective parameterization. So I'm going to speak briefly about each of these.
Am I the only one who hear this strange noise in the background? Everybody
I also hear it.
Yes, it's the sound of a stream, and it's meant to relax you while you listen to us talk.
Okay, but it just I couldn't hear you very well, so sorry.
Yeah, sorry about that. I'm not sure we can do anything more to quiet that. Next slide, please. The first accomplishment of Dezső's was introduction of variational data assimilation to the NOAA high-resolution regional models. And this had to do with the rapid update cycle, introducing variational analysis to this peculiar isentropic vertical coordinate that was described in a paper in the MAP journal in 2003. There was a lot of help in doing this effort with Steve Wygant from Boulder and also with colleagues from NCEP. Next slide. A second accomplishment was application of a larger data assimilation system, the grid point statistical interpolation, to the regional models. Dezső did this with our colleague in Boulder, Ming Hu. Ming continued that work after 2009. One critical part of that was taking this GSI data assimilation code and moving it from an IBM environment to a Linux environment. This was absolutely essential for GSI to become a community code and really sort of changing the landscape for data assimilation in the United States. Next slide, please. Dezső was critical in strengthening our ties in many places in the United States, but certainly with NOAA and with the National Centers for Environmental Prediction. This is a picture here with many of us at the house of Jim Purser, just a few months before Dezső died, with Ming Hu there, Steve Wykant, Dezső, and myself. Next slide, please. So we had these really 3 hourly updated models over the last 28 years. The RUC model, the rapid refresh model, more recently using the WRF and GSI, and now more recently still the HER model at 3 kilometers from 2014. But Dezső's work was critical in developing the data assimilation that supported each of these, and even the HER model now. Next slide, please. A third contribution from Dezső was working with George Grell on a new ensemble-based deep convective scheme. Again, this is sort of took advantage of Dezső's knowledge and innovative thought about application of statistics and really advanced mathematics in the representation of deep convection also. This was published in an article in 2002, but really was the basis for the more recent Grell and Paeta scheme, which is used across many models in the United States and even other countries, and in the rapid refresh also. Next slide. Before he came to work with us, Dezső did complete this masterful statistic application in meteorology. It's a little bit like the book by Daniel Wilkes that maybe some of you in the United States have used, and actually another one by Hans Panofsky. This version was published only in Hungarian, so that's too bad, but it showed also Dezső pulled in things across many different countries, including Lev Ganjian, that he worked with for a year. And so you can see in the top there the references in Russian. So he met with Lev in Leningrad then, that's what it says in Russian, and many other aspects. So it was an important contribution to statistics. Next slide. In summer 1999, this is a picture of Tom with John Brown and myself at Dezső again. I think the closeness that Gabor spoke of was uniform also across the ocean with us in Boulder. An example of this shown here. Next slide. So this is kind of a history of our hourly updated models with the RUC and RAP and HER. The changes that are shown in red here are ones for which Dezső's work was critical, moving to a variational scheme in 2003 with the RUC, introducing a new cumulus scheme in 2008. And then in 2012, this is of course after Dezső's death, but his work with GSI was really an enabler for being able to use GSI with the rapid refresh, which replaced the RUC in 2012, and even the implementation in 2014 of the 3 kilometer HER model. Next slide. These are some of the articles that Dezső had a key role in, and I better not roll through them too quickly, but notice the next to bottom reference there. It's an article about the RUC model in 2004. Dezső was the second co-author on that, which was very appropriate. It was a NOAA research paper of the year in 2004. And I also want to mention a paper in 2016. Dezső was not a co-author, but this is about the rapid refresh using the GSI, which Dezső enabled to take place. Next slide. So this is a group of all of us when the HER model, the 3 kilometer storm resolving model, was implemented in 2014. So quite a group of people here, but note on the lower left here, this is what I've shown before, that Dezső was really had a key role in this development for the ongoing high resolution data assimilation at NOAA. And with our group, personal knowledge, but also scientific enabling and teaching to do that. Next slide. So again, these are accomplishments of Dezső. There actually is a biography that Tom Schlatter and I and Andras and Gabor and Patricia all together wrote in the Bulletin of American Meteorological Society. You can find it there. And then skip one more to one last slide. This is a slide picture that I asked Dezső to do. We had some construction material lying around in 2004. So I said, Dezső, could we take a picture of us? I think this is typical for all of us. All of us learned so much from Dezső. He was a master teacher. He was a master colleague, and he was a close friend for many of us at NOAA and obviously around the world and certainly in Hungary. So that ends my presentation. We're grateful for Dezső, but also this award, which we're about to give now, is an important one and also a time to remember Dezső. Thanks very much.
Well, thank you very much, Stan, for your nice introduction and also for your heart-touching words. I think after this introduction, you can all see, even those of you who didn't have the chance to personally meet Dezső, you can see why we decided more than 10 years ago, when Dezső sadly passed away, that we establish an award to remember and celebrate Dezső's scientific achievements and also his pioneering role in numerical weather prediction in Hungary. The award was established in 2011, and since then 8 young scientists have received it for their work related to either numerical weather prediction or dynamic meteorology, the fields where Dezső was a real expert. Every year, the winner of the award is decided by a small committee that consists of Dezső's daughter, Patricia, and a few of us from this year, including Stan Benjamin, a few former colleagues and friends of Dezső. During this award ceremony, every time we ask the awardee to present their award-winning research or scientific paper. This year, the winner of the award is Noémi Sarkadi. Noémi is an assistant professor at University of Pécs. She studied at the Eötvös Loránd University of Budapest, where she graduated from meteorology. Later, she got her PhD at the University of Pécs, where she's now an assistant professor at the Geology and Meteorology department. She got the award based on her scientific activity, especially for the research and development activity carried out using the WRF model. In this work, Noémi and her collaborators introduced a microphysical so-called piggybacking method to better understand the interaction between the model's cloud microphysics and dynamics. So now, Noémi, I would like to ask you to give a summary of your work.
Thank you for the introduction, and I'm sharing my screen and also start the presentation. So I'm warmly welcome all the participants in this meeting. First of all, I would like to express my gratitude for the honor to being awarded for this year or in this year. In the following about 30 minutes, I would like to present the idea and also the method of the technique on separating microphysical and dynamical effects on cloud and precipitation formation processes. But before I'm going into the details, I definitely would like to thank all of my colleagues and co-authors who was involved in this research and model development on separating microphysical processes. During the presentation, I will give a short overview of challenging aerosol cloud interactions as one of our motivations, and then introduce the piggybacking technique, just try to make it in briefly. And subsequently, I will present the main points of our research paper and then conclude the findings with a brief outlook on our future plans. The main motivation behind this work was to understand better how the different microphysical and dynamical processes interact with each other, and what the result of this interaction on cloud and precipitation formation in nature. I'm sure that I do not need to elaborate on how the aerosols effects in atmosphere or effects in atmospheric processes directly or indirectly. On the other hand, it's need to note that in several research papers prove that there are some questionable points how the aerosol impact the cloud formation processes. It's clear at some point if we increase the number of the aerosol particles in the atmosphere, it can cause the increase in the number of the cloud droplets coupled with the decrease in precipitation efficiency, so can increase the lifetime of the clouds. It is especially true in warm clouds. However, the aerosol influences are even less well known in mixed phase clouds when ice is also presented. Just in the case of convective cloud formation processes, if we increase the CCN concentration, it can result higher amount of precipitation, and also it can longer the lifetime of the convective clouds. If the CCN concentration is low, so we can, when we talk about pristine conditions, it means that mostly larger water drops are formed in the clouds. This means that less ice and even less supercold water can reach the 0 degree isotherm, while the high CCN concentration means that the mean size of the water drops are smaller, so they can reach below 0 degree in larger concentration. And due to this larger concentration, the freezing and the latent heat release from the freezing, and also the melting of the higher amount of ice particles can cause larger temperature difference between upper and lower troposphere and upper and lower part of the clouds. It can strengthen the updraft and can cause the formation of newer clouds, and also can initiate new cloud formation processes. At the same time, also the latent heat release from the freezing can slow down the condensation and either can initiate evaporation in the clouds. So in polluted air, as a result, the convection can enervate, especially it's true in warm-based clouds. So this is some problem or problematic part. How can we separate these effects in convective clouds or even in numerical modeling of clouds. In order to understand better these processes, a relatively simple idea was created and introduced by Wojtek Grabowski. This is the piggybacking, or we can refer as master-slave technique. On the right hand side of the slide, you can see the schematic picture how the piggybacking simulation works. The main idea behind, or the main point of this approach, is to applying two sets of thermodynamics variables, just like potential, temperature, water vapor, and all other variables that describing the microphysical particles, just like aerosol, cloud, water, or rain, or any other precipitating particles, but we do it in a single simulation. The first set of the variables are working like a normal numerical weather prediction model. So the first set of variables coupled to the dynamics, and that's why we call it as driver, because it drives the simulation. On the other hand, the other set of variables are only affected by the main flow generated by the driver and undergo on the same physical processes. Instead, just like phase change, fallout of the precipitation, or interaction with surface fluxes. However, this set is not interact with the dynamics, do not affect it, do not has any local effect on changing local buoyancy and velocity field. So the only difference in this simulation that the thermodynamical is in the thermodynamical variables. It's important that in this piggybacking approach, we need to have a second simulation in which we switch up the thermodynamic sets. So the first was the driver, on the second simulation should be work as a piggybacker. So in which this switching we can expect different flow realization, because the two thermodynamical sets interact with the dynamics differently, and because it's modifying the buoyancy of buoyancy of the flow, and also we can separate the impacts of the physics. For example, if we change the CCN concentration, or even using different microphysical schemes, or just modifying some other microphysical parameters describing the size distribution differently in a scheme, or change the terminal velocity of the particles. So it can has a noticeable difference between the driver and the piggybacker set. If we just checking and see the difference, if we compare the driver and the piggybacker set, it's something that caused by the microphysics, because the dynamical parameters, so the flow, are the same in the two simulations. However, if we compare the two drivers of the first and the second simulation, we can observe the impact of the given parameter that we changed on the flow dynamics. It's a simple example for this change is how the microphysics affect the surface precipitation. So if we change something in microphysics, the difference between the driver and the piggybacker setup represent how the surface precipitation increase or decrease on the same flow due to different microphysics. While if we're comparing the two drivers, then we can see how the surface precipitation changed, including microphysical and mostly microphysical dynamical interactions.
Sorry to interrupt. I think we have a question from somebody.
Yeah, I don't know whether we should have questions after the presentation or Noémi, what is better, if you can interrupt you or?
You can interrupt me. I just do not see if you interrupt me. So please.
Okay. So Tom, I think you have a question from a few slides before.
Okay. So what was the question, or what is the question?
Can I suggest maybe to put any questions in the chat, and then we can address them at the end? Thank you.
Okay.
All right.
Thank you. Okay.
So go on. Thanks.
Okay. Thank you. So this piggybacking methodology was successfully applied in several cases, but usually more simplified model setup in a kinematic framework, not in a complex weather forecast model. The main goal of this research was to implement this technique into a widely used numerical weather prediction model. This was the Weather Research and Forecast, or WRF model. In this presentation, I would not talk about the technical background of the implementation of this technique. But please believe me if I say that it wasn't an easy ride all the time. I just showing you in this slide the first one of our first results in an idealized 2D simulation. I really do not want to go into really deep details on this figure. In this case, it was a microphysical piggybacking applying two different microphysical schemes. One was the Bach and one was the WSM6 Bach scheme. These are the domain averaged values of temperature, water vapor, and microphysical particles and microphysical parameters in a difference field. So the blue and the red lines related to the two different simulation. The first, when the Thomson drives the WSM6 piggybacks, it's in blue colored. The red colored lines represent the simulation when the WSM6 drive and the Bach, the Thomson piggybacks the simulation. If you just check the figures, all the lines are somehow mirrored to each other, and in some cases the difference is really small, but in some parts there are higher differences in the fields. These major differences come from the different flow realization and its interaction with the microphysical processes. If we assume, or somehow if we can change that the both simulation run on the same flow, so when the Thomson drive and the WSM6 drive, if we assume they should work in the same flow realization, the difference fields or even these lines should be absolutely mirrored to each other and only representing and showing the differences on the different microphysical parametrizations. And it's also obvious that if we apply the same microphysics scheme as the driver and as the piggybacker, there are no difference would occur in the simulation, because the microphysics and the dynamics should be the same in both cases. After small sensitivity studies, we started to focus on more complex problems. One of them was a 2011 MC3E school line case study. This case study was, this case was used because it was already simulated by using the verve also with bin microphysics and bulk microphysics schemes. And we had, in this case, previous model experiments and observations were available. The table here contains the main case setup for the simulation. We used two different microphysical schemes, one bulk, it was the Thomson scheme, and one bin scheme, it was the UPMB University of Page and Carbon scheme, and it was changing between bulk driving and bin piggybacking the simulation, and then switching bin drives and bulk piggybacks. This small animation shows a bin driver evolution of cloud or hydrometeor, total hydrometeor mixing ratio. So it's just a nice animation about the school line formation. The setup was only differ in the microphysics schemes. There were no any PBL or radiation physics code when we run the code. The initialization of the school line was take place with random temperature and water vapor perturbations on the middle of the domain, as well as with U-wind convergence. The same random perturbation and same wind shear or convergence were used on same setups. So one simulation with bulk drives and bin piggybacks, and the same random perturbation was used in bin drives and bulk piggybacks. And we have three ensemble members in this case study. In this case, we would like to demonstrate how the piggybacking approach can help to determine the important role of dynamical microphysical interactions in forming a transition zone in a school line. So about the results. This is a figure about simulated and observed line average and line average vertical cross-section and horizontal cross-section of the radar reflectivity field. On the upper two panels, on the first row showing the observed gridded next rod reflectivity, and from second to fifth row there are the model simulations. If we check the first column, it's showing the line average reflectivity field of the simulation at the end of the simulation. As we expect, and as usually, both schemes can produce a nice school line with definite convective region and also a definite stratiform region. However, as you can see here in the observation between the convective core and between the stratiform region, there is a transition zone which not presented in the case of the Thomson driving scheme, and it's presented in the UPMB driving scheme, and also not well defined and not presented when the UPMB piggybacking and the Thomson when the Thomson piggybacking with the UPnB generated flow, it's also nicely form the transition zone, as we can see on the observed radar reflectivity at around 2 kilometer height of behind the convective core, which is well captured by all the models. The transition zone only slightly overestimated, but definitely formed in the UPnB drive setup. And all the ensemble members producing similar behavior. The results in the case of the bug driver and the pin piggybacker, we started to think about what causing this difference, that the Thomson screen drives simulation, the reduced reflectivity region is not formed. Some argue that the formation of the transition zone is a result of the size sorting of the particles with given sizes and densities, and these are advected from the convective core. If the size sorting is the main reason for the transition zone formation, then we should expect that the bin scheme will form the transition zone regardless it's driving or it's piggybacking, and the Thomson not presented when it's just only piggybacking the simulation. But we found that it was not the same, or it was presented by the Thomson scheme and not presenting the bin piggybacking. So it means that the transition zone formation is not only a purely microphysical mechanism, but also there is some microphysical dynamic or interaction. If we just check, it's also an animation. This is the total hydrometal or mixing ratio and different ensemble members. It's enough to focus on, for example, it's just missing. Okay. Sorry. It's just missing the slide. It was just about the animation that in the transition zone, in the Thomson-driven simulation, we had more hydrometeors in the transition zone that can cause the higher radar reflectivity was measured. This figure shows the cross-section of the vertical velocity with the simulated radar reflectivity contours for in the rows, the second, the fourth, and the 6th hour of the simulation. All of them is plotted relative to the storm leading edge. The key point is that the spatial distribution of this vertical velocity differ between the simulations driven by the bug and the bin scheme. However, if we only focusing on the main circulation pattern in the two different setups, it just really slightly differ from each other. But you can see definitely that the UPnB drive and the Thomson drive simulation, the bin produces stronger downdrafts below 5 kilometer and weaker updrafts above this level in the transition zone. However, in the case of the BAL scheme, is has higher updraft velocities above 5 kilometer height and lower downdraft below 5 kilometer, which is close to the melting layer. So the transition zone, so that's why this different vertical velocity field help form the transition zone in the case when the bug scheme piggybacks. However, the size sorting is not well represented in the bug schemes, and also the velocity field is more important in this case because the bin piggybacking are not able to produce also the transition zone. However, the microphysical size sorting effect can easily describe in this detailed microphysics scheme. On the next slide, it's a little slow. Okay. Okay. It's just missing a slide about the precipitation. In the scoreline case, both bulk and bin scheme at the end of the simulation produces almost the same amount of accumulated surface precipitation at the end of the simulation. There was a little difference for the drivers when the bulk microphysics produces more rain during the initial 2 to 3 hours, but then there was a switch between the bin and the bulk schemes, and this also describes that the key role of the microphysics dynamics interaction has an effect on temporal evolution of the precipitation, but do not affect the total amount of precipitation in this case. The second case was a daytime convective development over tropical land surface, which was also well known from previous studies. It was a large-scale biosphere atmosphere or IBA case field project in Amazonia. This case study was also used in previous piggybacking simulations, and we choose it to check how the CCN concentration changes effect on surface precipitation and cloud evolution in this case. We assume 2 different CCN concentrations, pristine and polluted conditions, and only the bin scheme, the UPMB microphysics was used. The initialization of this model was set up with random temperature and moisture moisture perturbations initially, and also a driven surface sensible and latent heat flux through the total simulation, starting in 7:30 local time and reaching its maximum around noon, and turn back to 0 just before the end of the simulation. Okay. Okay, probably I restart the presentation because I had some problems.
It's all right, go ahead.
Yeah.
So in the meantime, if you can see
Yeah.
the chat window, Stan
Yeah.
has referred to the paper of Noémi, so you can find on internet that link where their article is can be seen. Okay.
Yes, I'm starting here. So these are the precipitation differences observed in this ABA case study. The left-hand side panel shows the different simulations. It has 5 members, so it's probably not well seen. There is some gray shades showing the ensemble spread, so there's no big difference between pristine and polluted cases when polluted drives or pristine drives the simulation. I would like to focus on this figure. You can see here the black lines related to the polluted case driving and the red when the pristine case driving. As you can see here, at the initial first part, when the transition from shallow to deep convection take place from the middle of the simulation and reaching close to the dissipation stage, until this point, the pristine case produces more precipitation, and the polluted case at the end producing more precipitation than the pristine. But if we just comparing the drivers and piggybackers, so the same colored solid and dashed lines, the pristine case every time producing more precipitation than the polluted cases. But it means that they are forming on the same dynamical structure or the same flow realization. And if we assume that there is different flow, it means that the dynamical microphysical interaction causing the difference, that the precipitation in polluted cases will be higher at the end of the simulation. This figure shows the cloud evolutions through the changes in cloud fractions in the 3rd, the 6th, and the 9th hour of the simulation. The first row shows the polluted driving, and the second row shows the pristine CCN concentration driving simulation. Until the deep, when start to developing the deep convection, there's no big difference between the two setups. But at the end, in the case of the dissipation stages, we can see that in the case of the polluted driving sets, we have higher cloud fractions above or near to 10 kilometer, which means it can some effect of the microphysics, because in the polluted case, as we will see, there will be more ice particles because of the differences in also the cloud water number concentration in this case. If we just focus on the other hand, and also it's an advantage of the piggybacking methodology that we can do point-by-point comparison of different simulations, because we have all thermodynamic variables for both drivers and piggybackers in each grid points. The slides on the left-hand side shows how the supersaturation changing between polluted and pristine, if it's driving or piggybacking in 3 kilometers, so below the melting level and above the freezing layer. In the polluted case, we get what we expected. We have lower supersaturations and higher supersaturations occurred in the pristine case, and it also has an effect on buoyancy. But as we can see here on the right-hand side figure, the activation CCN is, or the available CCN that activated is, the number is not changing, even if we increase the supersaturation, but there are really similar results, regardless to a pristine piggybacking the simulation. This is the red colored, or it's driving the simulation. This figure shows the buoyancy plot similarly to the supersaturation differences, because it affects the buoyancy and thus the vertical velocity. This is a key point. The buoyancy differences here in 3 kilometers are large and often and significant fraction of the driver buoyancy, with larger buoyancies and larger differences occurring correspond to higher vertical velocities. This is represented by the more reddish colored dots, and we can see definitely that the difference is not symmetric, and this is suggested that there are differences in cloud dynamics between the polluted and the pristine case, in agreement with the supersaturation differences. And my final plot related to the results is about the microphysics. On the left-hand side, the liquid hydrometeors, so cloud water and rainwater, and snow and ice on the upper panel of the right-hand side, and graupa on the bottom part. You can see here this smaller amount of cloud water related to the pristine case, so the red solid line and the black dashed line is almost overlap each other. It does not matter what is the dynamical flow in this case, and this is the polluted case. In the polluted case, we have more cloud water formed on the available CCN, and this difference also take place in the upper or above the freezing level, because we have more ice particles in the case of the polluted cases, but there is some effect on the dynamics, because the pristine piggybacking scheme, or when the pristine is piggybacking the polluted driven case, it's also producing more ice in the above freezing level. So it's really important to understand how can we separate the different aerosol cloud atmosphere interactions, especially if there's some dynamical effects that then can take place not just in daily weather forecast but in climatological ways. These results are published in a paper in Journal of Advances in Modeling Earth Systems with the title of Microphysical Piggybacking in the Weather Research and Forecasting Model. And it's just a short or brief note that including the radiation, PBL, and other microphysical and physical processes. So a real case piggybacking will be presented on the upcoming AMS on session 4B.3. And I would like to thank you for your attention with the same citation that was that's on the plaque of the Dévényi Dezső Award, and it's also the first presentation start with this citation. So we start and end with the same sentence. Thank you for your attention.
Okay, thank you very much, Noémi, for this nice presentation. Now the floor is open for questions and discussions. So there was some comment in the chat window. For those who can't see it, I will read it. So this is from Stan Benjamin. It's interesting that you didn't allow radiation differences, but isolated the thermodynamic difference, if I understand correctly. So can you explain why it was so?
Yeah, because in this case studies, we do not assume any radiation. So only microphysical dynamical interaction was taken into account. So no radiation, no PBL, no other physics was turned on in these simulations. So it's the next step.
Okay. So any further questions? If you can do it either in the chat window, or you can unmute yourself and then say it verbally.
I'm wondering if Tom has had a question. His hand is still up. Tom, did you have a question in one stage?
No, probably it was just by accident.
I'll ask another question. Noémi, thank you. Köszönöm. You know, you have all these great results in it, really amazing to look at the pristine versus the polluted environment. We already knew a little bit, you know, if we have more CCN, that we will have this effect of less precipitation and more cloud potentially. But it seems like the detail that you have in this study it goes beyond that. Can you summarize what you've learned about polluted versus pristine environment? What's new about that?
Yeah, it's more about how so the cloud dynamics below the freezing in this case have a relatively small impact on warm rain processes. So the warm rain processes are mostly forced by the microphysics and the microphysics parametrization, and also the CCN concentration. However, if the ice phase, so ice is occurred, and we include the ice, the microphysical and dynamical interactions, how the updraft velocity formed, it's differ in the polluted and the pristine cases. For example, in the Graupel, if we just, I think here, it's still, I'm still sharing my screen, yeah? So here in the Graupel mass, the driver and piggybacker difference, so the solid and dashed lines, it has some, you can see here that the driver, it does not matter it's pristine or it's pristine or polluted, was the driver in the mid troposphere or in the middle troposphere. It's changing the sign here, so there is a difference that it comes from also that the freezing of the raindrops is the dominant process for groundwater formation in lower temperatures. However, if the temperature is higher, the dominant process of the formation of the growth of the groundwater particles is the riming process. So, and also the riming it's based on the available water vapor or cloud water as well. So if there's not much cloud water above freezing level, we won't have as much groundwater particles. And also in a convective cloud, if we have more ice, we will have more precipitation on the surface, I think.
Thank you.
You're welcome.
There's another question from Sean Mudzek.
Yeah.
Can you see Noémi, or should I read it?
Yeah, I can see. So, would you like to that I read?
Yeah, please.
Okay.
Please.
So, really interesting talk. I was surprised by your result regarding to the transition zone in school line case. Do you have any guesses as to why the vertical velocities are so much stronger immediately behind the convective core in the simulation with the Thomson scheme driving compared to the simulation with the Bean scheme driving? It seems like it is those strong vertical velocities in the Thomson driving simulation that prevent a clear transition zone from developing. Yeah, that's true. What causing it? It's still questioning. I'm not really sure, because the main circulation, so the main where it is, I was too fast. So the main circulation pattern, and also we are generating streamlines, are not really differ in these two cases. It's something I think in the initial dynamical reaction on the changes in the microphysics, because in the Thomson scheme, in the second hour, it's still something like a spin-up time for this simulation, or almost at the end of the spin-up. But in the first few hours, the microphysics is more important in the case of, for example, in the surface precipitation. And because of it, the microphysics, I think, overact the dynamics and the force of the microphysical changes. So the release of latent heat and the temperature difference caused by this the releasing latent heat can cause the strengthening of the updraft velocities, and that causing the main differences, which is not after that point. It's probably we do not have enough run hours, so we have only a 6-hour simulation. Probably after 12 hours, these differences can absolutely eliminated, and because the dynamics and microphysics can equalize its effect on the formation of precipitation and also the school line transition zone. I hope I answered the question.
Okay, thank you. There is another question. Dave Turner raised his hand.
Hi, Naomi. Very interesting presentation. More of a bit more of an abstract question for you. I've always seen piggybacking done and applied to microphysical schemes. What would be is there an advantage to actually testing other schemes with this type of approach? Could you test, for example, a PBL scheme using a piggybacking approach to look at the impacts that you might see from a different PBL scheme?
We do not did it yet, but this is our next step. First, in a real case piggybacking, we are just turning on the radiation and the PBL schemes. But on the next step that we would like to run physical piggybacking with using, for example, changing the PBL schemes and leaving the microphysics the same way. So we did not do it yet, but it's also planned to do it.
Thank you.
András?
Yes, thank you, Noémi, for the interesting presentation. I have two questions actually. One is more serious, the other is less. So I understand from your talk that your research contributes to the better understanding of precipitation and cloud processes, and practically for the microphysics and dynamics interaction. Do you have any examples how, in practice, from the NWP operational weather prediction practice, how this research can contribute to operational improvements in NWP? I understand that you have better understanding, so you improve your schemes accordingly. But do you have any examples how this was done in practice, or it's more at the moment it's a research kind of thing, and then it will be seen later? That's number one. And number two is a more practical. It's I see your co-authors are coming from all over the US and different universities, institutes, even somebody from Australia. So how could you work together in one practical way with all these people? I guess, especially with the pandemic. So would you shed some light how this cooperation could go? It could be quite exciting and interesting, maybe, for the others as well. Thank you.
Yeah, thank you for the questions. For the first question, I think understanding it's something that it's really important, because if we know that what's causing the difference, we can improve our models. I'm not sure, and as far as I know, there's until this point there's no real usage of the piggybacking method in numerical weather prediction yet. But I'm sure that if we spread how can we use this method, it can help us to improve the numerical weather predictions. On the other question, yeah, this work, it was a long ride. I started to work on implementing the piggybacking method into WRF in 2017. So, and it's partly I had a break because I was on maternity leave, and after I came back, I continued to work, and all of my co-authors at some point they started to work on implementing the piggybacking method, but they are just stopped at some point, and we are sharing and they are sharing their thoughts what was the way was not working in the implementation. So so we go through so the main work of the implementation was done in 2018 and in person before the pandemic, and after that we had Zoom meetings, mostly online, in a monthly schedule. So that was the main part. And after the pandemic on this year, I was also visited my coworkers at Ankara in Border. And I will go again in January.
Okay, thank you.
Thank you.
Okay, so thank you very much, Noémi. So if there are no more comments and questions, so thank you all for your participation. Thanks especially to Stan and Noémi for their talks. And at the end of the official part of the meeting, we would like to encourage further young scientists for the future to apply for this award. Even more practical, operationally targeted implementations, if they have something to do with NWP, they would be welcome. So not only research, theoretical studies are welcome for this award. So I think now the official part of the meeting is over. So we would like to ask maybe those of you who knew personally Dezső, if you still have time and can stay here for a informal chat, that would be nice. And thank you, everybody.
Thank you.
Thank you